So what I'd like us to consider here is the whole periodic table. This is the whole periodic table, as you can see. And the whole periodic table, what is highlighted is only what you have as your let me see if I can get something for writing or a pointer. So what you have here as your periodic table, where the cursor is moving, where you have labeled elements, are your transition metals. The blue block is your inner transition metals, and they are labeled as group 3. Group 3B consists of scandium, yttrium, lutetium, and so on. But group 3A is our usual group 3A, which is boron, aluminium, and gallium, and so on and so on. So B, 4B, titanium, and so on, 5, 6, and so on. Then you have your 1B. Then we have seen that 2B are included in the transition metal block, even though they don't behave as transition metals per se. So the next thing we need to understand is the trends in the periodic table. Transition elements have a number of characteristics that differentiates them from the main group elements. First characteristic is that all of them are metals. But when we look at the main block or the main group elements, we see we have gases, we have liquids, then we have metals and non-metals in the main block group or in the main group block, whereas in transition all are just metals. That's why they call them transition metals or TMs. They have very high melting and boiling points, and therefore they are very hard solids, except for a few. Okay, you can see their melting points range in thousands. Then several transition metals, except for group 3B and 2B, have several oxidation states. For example, vanadium exists as aqueous ions in all the states from +2 all the way to +5, meaning there is +2 vanadium, there is +3 vanadium, there is +4 vanadium, +5 vanadium. And all these oxidation states have different colors. This is depicted in this photograph or figure 22.2, whereby you have those transition states of the elements starting from pale yellow, then you move to bright blue, gray blue, violet. Of course, when somebody writes vanadium here, vanadium O3 minus, it's very easy for you to do your calculations and see how it works. For example, vanadium 0 for oxygen that. The state for vanadium there will be X plus 3 times -2 should give us -1. We know that from high school how to calculate oxidation state of an element within a compound. What shall we get? We get that X plus, no, -6 is equal to -1. And therefore X is equals to 6 minus 1. So here vanadium is +5. You can do the same for that one, which will be X plus -2. One oxygen is -2. Let me rub to create some space for the working so that we can remind those who have forgotten and they are daydreaming. So it means we have x plus minus 2 should give us positive 2. Therefore, the next thing should be x is equals to positive 4. So here is 4. This was 5. And so on and so on. Then the other one is 3. Then this other one is 2. Yeah. The last one there is 2. Having seen this, I hope it makes sense to all of us. It should be an introduction that helps us understand even the basics we may have forgotten from high school or undergraduate. Okay. So transition metals are involved in oxidation reduction reactions or redox reactions. Then number 4, their compounds are often colored and are paramagnetic, but most compounds of main group elements are usually colorless and diamagnetic. So I hope we are able to see a few differences between main group elements and transition elements like color, oxidation states. What else have we seen? Paramagnetic and diamagnetism as a difference. We have also seen, they have several oxidation states, high melting point, and they are all metals. Let us see some trends of this of the transition metals in the periodic table. We look at melting points and an overview of is that the metals, we've already seen high melting point, conduct electricity, obviously. They are shiny or they have metallic sheen, then they react except in various oxidation and reduction reactions, except for a few. Then they react with various oxidizing agents to give ionic compounds except for silver, gold, and platinum. And these 4 elements usually resist oxidation, and they are very useful for making jewelry or for decorations. So these pictures just help us to appreciate what transition metals can be used for. First, in art, here they're used for coloring, that's artwork. Then here they're used for pigmentation, especially in glassware. Here again, they're also part of the coloration we see in precious stones like corundum, azurite, turquoise, amethyst. Another important thing we need to appreciate or even remember is electronic configuration. And given that transition metals are elements from the periodic table, we need to understand their electron configuration. The electronic configuration of transition metals is usually in the form of a noble gas core. Let me get a pen. A noble gas core followed by N minus 1, then the DNS. So for example here, the noble gas that comes earlier is argon. For this period 3 here is argon. So for this, the whole of this period 3, it will be argon 3D 4S. So the N is corresponding to the group number. So it's in group, not actually group, but period. So this is period 4. So our D is 3D, and the other one becomes 4S. If it's in period, this should be period 4, sorry, this is not period 3, it should be period 4. Okay. And period 5, therefore, will be krypton. And of course, if we go back to the periodic table, we'll see where argon and krypton occur. They actually occur before each. Okay, this periodic table is incomplete, so we can't use it, but you'll find that argon comes here. Argon will be showing up here so that it is used in this group. Then krypton comes there. It is used in the next group. Okay. So that if I'm writing for titanium, I'll start with argon. Then we shall see that this represents D1 and this is D2. So it will be 3D1. Then S2. Okay. If I'm writing for osmium, for example, osmium, I'll pick the noble gas there. Then osmium will be this is 5D. Osmium would be a 5D. Okay, 5D, 5D. So this is D1, D2, D3, D4, D5, D6. So osmium is D6, S2, 4S2. So you can actually guess what silver will be. Silver automatically will be a D7, 8, 9. Silver Ag is a D9 and it's still in 6, so it will be N minus 6, so it will be 5D9. So in other words, we should be able to write the outer orbitals of transition metals. The outer orbitals are the most important. We don't mind so much about whether you write 4s, 4s2, 3d. Of course, once we are able to master that, this is D1. Sorry, my pen has disappeared. This is D1. Everything here is D1. Everything there is D2. Everything here is D3, and so on and so on. Meaning that if I'm writing for example, for tungsten, I'll write it as it should be a D4. It will be D4 S2. So what is the N? This is 4, 5, 6. So because my N is 6, therefore this will be 5. And this will still remain 6. Remember, it is N minus 1D, then N. Okay, that's how we do it. So at your own free time, you can actually do it now and see whether you can get for, let's say, a random one, like copper. Okay, copper. Okay, what's copper? This is D5, D6, D7, D8, D9. Copper is therefore D9. So if I clean here, I can do for copper is D9. Copper is D9, S2. But it is in which period? 4. So it will be 3D9, 4, S2. So what I've just written there is the outermost orbital, which is most important when we are studying transition metals chemistry. So another thing is Nm, or the number of electrons initially in the metal, and what happens when a reaction occurs. So initially, we can actually know the number of electrons specifically in the outermost energy level. That's our concern. What is in the S and the D? So how do we do it? As I told you, in the first column, they're usually called D1, then D2, then D3, and so on. However, each element has also a full S2, a full S2. So in total, you just add what is in the D and what is in the S. Like here, it will give you 4 because it's D2 plus S2. This is D1 plus S2, okay? And here will be what? This is D3, D4, D5. So D5 will have 7 because it is D5 plus S2, and so on and so on. So this is the abbreviated form, but remember, for exam purposes, I'll just provide the periodic table, this one. Okay, so for exam purposes, I'll provide such a periodic table, of course, minus my drawings. My drawings won't be there. It will be a clean periodic table with no configurations. So it's up to you to get the configuration. However, the table here, this one, summarizes the configuration. You can see clearly D1, D2, D3. This is supposed to be a D4, but they have written the stable form. It's D4S2. Okay, this one. But they have written it in the most stable form, which means one has been borrowed from S and given to the D so that you get D5S1. So this again, now this one is D5, which remains the way it is because D5 is okay. Then D6, D7, D8, D9. For D9, what happens? They borrowed, because this is D9, S2, they borrowed one from there to make it D10, which is stable. Okay, then this is D10. So again, you are seeing the n minus 1 thing, okay, because this is period 4, which means n is equals to 4. So it should be D, our D will be n minus 4, 1 minus 4, which is 3, and then 4s. Then you go to the next period. This is the next period. This period now, you can see this is period 5. So this 4 represents n minus 1. Then this is 5 is our n. Period 6 is there. You just simply take n minus 1, which gives you 5 because this is period 6. Okay. So that is period 6. So the D becomes what? N minus 1D, which is 5, then NS, and so on. So not a big deal there. It's just a repetition of what I've already spoken about. Okay. So, okay. So here we've seen what happens as you move on. This is just a repetition. What you are seeing here is just a repetition of what is happening as you move across the period, as we saw here. So this is just showing what happens to the orbitals as you move across the period like that. That's what it is showing here. Okay. When you move from 3B, you have 4SD1, then you have S2D1, then S2D2, S2D3 as you're moving, which I've just shown in the periodic table. Now we have electron configurations and orbital diagrams. So we have just considered one period. So as you move again, you can see what is happening. It's D1. It's D1. Okay, I'm looking for that. So we have D1, D2, D3, D4, D5. Then you just fill your orbitals like that. So orbital diagrams should not be something difficult to draw. So you can see clearly again, the emphasis is where? The emphasis is in the outermost orbitals. So forget about the noble gas summary there. The important part is the one that is not in brackets. And we know D has 5 orbitals. 1, 2, 3, 4, 5. Then S has only 1 orbital, and therefore 4s is full. Then the D has only 1 electron. Then titanium, the same story is applied. It has D2, so D has 2 electrons. Of course, you fill 1, 1. Then 4s is full, okay? And so on and so on. So all of us should be able to write the orbital diagrams of transition metals all the way to the last one here. So we can see the last one here, which is full. Just a minute. The last one here, which is full. Okay. It's D10S2, so you just fill it. Then you can see our D9 there. You stabilize it by just making the D full. So remember, copper here is ordinarily D9, 4s2. So what has been done, you promote 1 electron there, you get a D10, 4s1, 3s, 4s1, 3s, 3d10. Now let's look at oxidation and reduction. All metals undergo a wide range of oxidation, by a wide range of oxidizing agents such as oxygen, halogens, and aqueous acids. If you remember, how do aqueous acids oxidize metals? If I have a metal, a metal like we saw in undergraduate or even high school, a metal plus an acid like HCl, what do we get? We get hydrogen gas plus a metal chloride, for example. So the metal chloride is +1 and hydrogen is 0. So it means the hydrogen that was initially here +1 has been reduced to 0, while my metal was initially 0 has been oxidized to +1. So that's what we know about oxidation reduction in form of electron exchange or transfers. So all transition metals except vanadium and copper are oxidized by aqueous HCl. This feature is sometimes undesirable, especially, for example, for materials like iron. We don't want iron to corrode easily, but of course, chemists have learned how to prepare steel, which is stainless or non-corrosive or non-corroding. How oxidation affects electron configuration. When a transition metal is oxidized, the outermost electrons are removed or lost. That is the 4s. The s electrons are removed. So the s electrons are the first ones to be lost. So for example, it's very straightforward. For example, if I'm losing, let's use just an example that already here. So for example, if let's say I'm dealing with titanium, where are you? Titanium is here. So if I'm dealing with titanium and I'm forming maybe titanium 2+, what happens? I will lose these electrons. So the configuration of titanium 2,1 will be 3d2 4s0. What about titanium Looking for the rubber, it's not coming through. Okay. So if I'm looking for titanium 3, for example, what will I expect in the configuration? So if I'm dealing with titanium 3 positive, what happens? The same titanium, it will lose first of all those two, followed by 1 there. So it will be 3D1 4S0. So that will be your titanium 3 plus. And therefore we can do even for cobalt, okay? For example, cobalt 2 plus. If I'm talking about cobalt 2 plus, then what will happen? It will, let me move it upward. No. Yeah. Cobalt, assume we are talking about cobalt 2 plus. What will happen? It will lose just those two. What about copper 2 plus? It will lose this one and lose one there. That will be my copper 2 plus. Copper 1 plus, it will just lose one electron, which is this one here. It will lose only that one. And therefore, copper 1 plus will be a D10 4S0, and so on and so on. So it's very easier for us to write, to be able to write electron configurations of transition metal ions. Transition metal ions often possess unpaired electrons, resulting in paramagnetism. Transition metals are frequently colored due to absorption of light that causes electrons to be excited from one lower energy level to higher one. So colors in transition metals are usually due to electrons moving from lower energy levels to higher ones. So we shall see this later when we discuss properties and bonding and how that is affected or affects the orbitals. So here we have a few things I want you to study. I'll give you just a few seconds to study. Okay. And so having studied it, we can see clearly that uh, when elements react with oxygen, we get mainly different oxidation states. For example, what is the oxidation state of vanadium pentoxide here? What is the oxidation state? If we do our calculations, we'll see what. Let's see what we shall see. It will be, we don't know vanadium, so we call it X, 2X, okay, plus minus 2 times 5 should give us a 0. So 2X plus minus 10 is equals to 0. 2X is equals to 10. X is equals to 5. So the oxidation state of vanadium there is positive 5. So it varies actually. You cannot really say it must always be positive 2. No. It varies with the transition state and stabilities, as we shall see much later. Then again, we are seeing different oxidation states when you form chlorides on this other end. Let me clean the whiteboard. So what about on this other end? We can see chlorides are forming. Again, once we have our chlorides, what do we get? You can see for vanadium, you're getting vanadium plus 4. Okay. Titanium, you're getting titanium plus 4. Manganese, you are getting manganese plus 2. Iron 3. Cobalt 2. Nickel 2. Copper 2. Zinc 2. Yes. What about reaction with HCl aqueous? We see again a change. We can see with HCl, you get positive 3 there, but with chlorine, you get positive 4. Of course, we know chlorine is a very powerful oxidizing agent. So what do we expect? Possibly, in some cases, higher oxidation numbers, but it's not a guarantee. Then we get higher oxidation number when you have chlorine than when you have HCl. Okay, you can see here it will be chromium 3, and here it's chromium 2 with HCl. Here it's iron 3, here it's iron 2 with HCl. So you can see the essence of a strong oxidizing agent affecting the strength of the oxidizing agent affecting the oxidation state. For example, with a strong oxidation agent, we get vanadium, we get titanium 4 here. But when we use a weak oxidizing agent like HCl, we get titanium 3. Okay. And in some cases, you get no reaction. Just look here. Okay. Okay, my pen doesn't want to go away, but in some cases you can see there is no reaction. Let's see where there is no reaction. Like in vanadium, no reaction, meaning that vanadium NR here means no reaction. So with vanadium, no reaction with HCl. But with a strong oxidizing agent, yes, there's a reaction. So you can see in some cases no reaction because the oxidizing agent is too weak for that type of a metal. Here again, we see the similar story, no reaction between HCl and copper. Of course, we know the electrochemical series, but we don't necessarily need to use it here. But again, it's a reminder again when we get here. So here we see some reactions of transition metals. We can see iron burning with oxygen in form of steel wool burning on a burner. Then we have the same iron reacting with chlorine gas. Then we see the same iron reacting with HCl. And you can see they will give us totally different products. Okay. We get, in the first case here, we get iron oxide, almost iron 3 because there's a lot of oxygen. Here, definitely chlorine is a strong oxidizing agent. We shall get iron 3 chloride. Okay. Those are the oxidation states. But here HCl is a weak oxidizing agent, so we get iron 2 chloride. Declare the oxidation number for iron, you'll find it to be 2. So in case of any background noise, you'll have to bear with me, of course, because I don't live on an island. Now, the mostly encountered metal ions have oxidation numbers +2 and +3. And you can always write the oxidation numbers. For example, iron, its oxidation number is, iron atom's oxidation number is this one, neutral before reaction. Then after reaction to form iron 2, we see what happens. You lose that, you lose those two. Okay. On the 4s, Then when you form ion 3, you lose 1, all the 2, then 1 from the 1 from the, you lose the whole 4 and 1 from the 3d6 to get that one. I've already talked about this, and we also get other compounds that have a range of oxidation numbers. For example, chromium, which is ranging from 6 to 4. So transition metals have a range of oxidation numbers. They are summarized here. I don't expect you to cram. It's just that we should know that they exist in different oxidation numbers. Trying to move this. For example, we can see that the element in the middle of the periodic table, or in the middle of the block, okay, the middle of the block has the highest possible range of oxidation numbers, manganese, all the way to 7, okay? Then it gradually reduces as you move away from the center of the block, or yeah, so as you move away from the center of the block, it decreases. As you move away from the center of the block, it decreases, so that the early and the late elements, these are the early and the late elements, have lesser oxidation states. So you already told that from this table, the commonly occurring oxidation states are indicated by red, and the rare ones with blue. And again, very important is that oxidation states, when they change, we also see color changes, because the electronics of these elements change. So if you are to draw the orbital diagrams of these elements of chromium 3, for example, you are to draw the orbital diagram. It will not be similar to chromium 6 here. Okay. Of course, these two are chromium 6, these two are chromium 3. However, they have different groups attached to them. Here you have nitro, but here you have chloro. Here you have chromate, here you have dichromate. So let us see the radius. How do the radius vary across the period for transition metals? And we are told that the atomic radius increases in going from the 4th period to the 5th period within any column. So let us see how it is happening. So you can see that period 5, let me use a cursor, okay. Period 5, or maybe a pen will be easier for you to see, and maybe I use red. So these two, period 5 and 6, you can see there, if we compare one corresponding group, okay, for example, that group where you have iron, okay, it goes all the way, you have iron, ruthenium, and osmium. What do we see? We see that iron is the one that is in period 4. This is for period 4, that one. While period 5 is that one, okay? then period 6 is the lower one. Okay, so it means this first value is for iron. Okay, then for ruthenium is that one, then for osmium is that one. So it means iron has the lowest radius in that group, followed by ruthenium, then followed by osmium. But that is expected because remember, you are moving from period 4, okay, period 4, like that, to period 5, meaning 5 energy levels. So that's very obvious. 5 more, if I move from iron to ruthenium, I've added 1 orbital already, okay? So it means I'll be having a bigger atom for ruthenium, then much bigger for osmium, just like we see ordinarily in the periodic table of the main group elements, okay? Now let us clean the board and move on to something else. So you are told covalent radius of scandium is 144, for example, but the one of yttrium is 140. Okay. And this information that we are being told about is here. Okay. And if you want to see it, it's again indicated in that graph. So we can easily see that this lower number represents our scandium. Then the next number represents our yttrium. Why? Because the subsequent addition of a shell of electrons. So it's additional shell as you move from period 4 to period 5 to 6, you're adding an extra shell, and that increases the radius. So let's see the other observation. The radius of d block elements in the 5th and 6th orbitals, 5th and 6th periods, are much smaller than corresponding elements. Let's see, what is that saying again? I'm thinking of some mix up here. Let me just read these two sentences so that all of us can see whether it's making sense or it's a mix up. All of the remaining elements of the 6th period have nearly the same covalent radius as corresponding elements in the 5th orbital or 5th period. So we have elements in the 6th period. Where is the 6th period? This is our 6th period, okay? Elements in our 6th period have nearly the same covalent radius as the corresponding elements in the 5th period. So there is, this is shown by the gray boxes. So I want us to look at the gray boxes to understand what is communicated for us here. Okay, So let me just rub here. So look at the curves for period 6 and period 5. You can see the curves are so close to each other, which means that their radius are not so different, okay? They're so similar, okay? See where I've put the gray boxes. I'm not able to, I don't know what has happened to my slides, but I think there is something that is not what I expect. So I will check again whether my sharing is going on properly, but allow me to complete at the, to conclude at that point so that we don't have many errors occurring, because remember, I'm recording online, I'm not recording offline, and anything could be amiss, and again we miss lots of this explanation. So what I want us to see clearly is that, let me use a pointer. What I want us to see clearly is that you can see those are close. You see the curves are close. So this and that are almost the same radius. Which are those elements? If we are keen, which elements are these that are here? It is zirconium and hafnium, okay? Period 5 and 6. So you can see that these are so different from titanium, okay? Remember, titanium is the one in period 4, but titanium here. But these two are very close in radius, okay? And we can read this radius of the graph. It's almost 145. The radius for zirconium and titanium is around 145 and 144, whereas that of titanium is around 132, okay? Then when we move here, okay, what happens? We can see that the radius for vanadium is around 122, whereas the radius of niobium NB and tantalum TA, both of them have the same radius, which is 130, almost 134 there, okay? Picometers, okay? So you can see that is happening they are so close, especially on this far end and this far end, but still they are much closer to each other, but far apart from the period 4, okay? And that's what we are seeing in that explanation. And in that as an observation, and we are asked to explain why is it so, okay? And I want us to see why is it so. So why is it so? Because the filling of 4f orbitals is accompanied by a steady contraction in the f5d orbitals. So I'll stop there because my slides are unresponsive. So thank you for that. I will continue in the next session. But I hope we've understood so far to that point, because that's where I'll resume from.